Hello and welcome to another episode of Carbohydrate discussion series. Today, Bharat Singh Patel will present how protecting groups affect glucosamine glycosylation. Let's begin the session.
As we know, the 4-hydroxy group of N-Acetylglucosamine derivative is very poor nucleophile, especially in the glycosylation reaction. So the lack of reactivity of this C4-hydroxy hampers the synthesis of very broad spectrum biologically important glyco-oligosaccharides and the glycoconjugates, in which glycosidic bond with the N-acetylglucosamine 4H are essential component. So in this regards, to such linkage strategy have been developed. So in this paper, what they have done, they have overcome that reactivity. They've taken three type of acceptor. So one is the N-acetyl C4-hydroxy acceptor, and second one to deoxy to azido group, and the third one 2-N-Phthalimido acceptor they have taken. So their aim was to determine the relative reactivity of these three, and also understand the why this one is the poor nucleophile, and how to develop or design new surrogate of the acceptor one. So firstly, we'll discuss the relative reactivity of the acceptor one. So in the same regards, they have taken this sulfoxide donor 4. They have pre-activated this sulfoxide donor 4 by using triplet anhydride in dichloromethane at -78 degree to form this intermediate triplet 5. So they have mixed this triplet 5 with 1, 2, 3 in separate system, and they were able to achieve the disaccharide with three acceptor. With acceptor 1, they got the yield of 9%, and with the azide one, the 2, they got the yield of 70%, and with the acceptor 3, with the Thaliamido group, they got the 58% of yield. So by seeing the observation, we can see this first one, the first acceptor, the estimate one, is the least reactive one. So to like since now they know the product of the each acceptors, so they have done the comparative study by using with the same donor 5, and they mixed all three in equimolar with the 5 in the standard condition. So the competition experiment, they observed that this 7, they got 10 times more reactive than the acceptor 1, and the third one, this third acceptor, they got in between reactivity between 1 and the 2. So by seeing the structure of the acceptor, since in the case of 1, there is a chances of hydrogen bonding with the intermolecular hydrogen bonding with this one, with estamide. So they modified the acceptor 1 by synthesizing the acceptor 12 and 14. So they started with the compound 9. They protected the 3-hydroxy group by using sodium hydride in BNBR. They got 10. And again, then they did the acetylation of this amine group by using acetyl chloride and presence of diisopropyl ethylamine in dichloromethane system. They got the 11. After the selective opening of the benzylidine group by using sodium triisonobiohydride, they got the acceptor 12. And similarly, they have protected this 9 by using sodium hydride BNBR in excess amount of BNBR. They were able to get this 13, and after opening up the benzylidine group, they got the 14. In one case, this is the N diacetyl, and one case N-acetyl 1 benzyl group. So again, they used this donor 4, and then they pre-activated the donor 4 by using triplet anhydride, and then they mixed the acceptor 12. and followed by the deprotection, and then succinic anhydride they use to further removing the whatever polar or the methanol will present, that will form the succinic ester. Then they can easily purify the compound. In the case of 12 means N-Acetyl one, they got the 47% of yield, and in case of the acceptor 14, they got the 39% of yield. So there was improvement of the yield with if you compare with the acceptor one with the N-Acetyl one. So to comparative studies, they mixed 1 and the 14 with the same pre-activated donor 4, that is ultimately form the donor triplet 5, that will produce the disaccharide 15, and the 6, the ratio was 1:2:2.2. So that means if you compare 1 to 14, 14 behave as a good acceptor compared to the 1, but they did not compare the 1 with the 12, because in case of 12, the partial de-escalation was happening, and ultimately that was leading to the 12 disaccharide. That means the product or the acceptor was forming, that was 1 only. So that just they compare with the acceptor 1 versus 14, and they found that the 1 was 12 and 14 are superior to the 1, and that was comparable to the phthalimide acceptor 3. But in terms of azide 1, 2, that those were inferior to the azide acceptor. But in the down the line, they have not utilized the 12 and 14 as an acceptor, because in case of 12, it was unstable in the amide condition, and the 14 it was forming, since presence of this 2 amide group is behave as a rotamers. So people have utilized only 3 and 4, that azide and the phthalimide, as a acceptor. Also, they looked for acceptor 16, which was moderate reactive compared, like in case of whatever donor they have taken, minosyl X donor, they got the alpha beta selectivity that was less, 5:1. But this was not utilized because the preparation of this 16 itself is a lengthy. That's why people just went with the 3 and 2 as a glycosyl acceptor. So till here, we do understand, like there is a less reactivity of N-Acetyl group compared to the phthalimide and the azide. So what could be the reason? So for that, they started with the NMR studies, where they have taken the acceptor 1. Acceptor 1, they took the NMR in the CD shell 3 at the same temperature, that room temperature, and once the concentration of the like acceptor 1 increasing, the chemical shift value of the NH proton is also increasing. That shows the intermolecular hydrogen bonding. So like as the concentration increases, that there will be more number of the acceptor, so there will be more hydrogen bonding, that leading to the intermolecular hydrogen bonding. To cross check the intermolecular hydrogen bonding, what they have done, they have taken the same acceptor 1, but they have studied the NH proton chemical shift value versus the temperature. So what they found, as the temperature is increasing, the chemical shift value of NH is decreasing. So here the linear regression of delta versus delta T plot found the concentration, they have taken the same 0.05 molar, that gave the reduced temperature coefficient of -2.1. In the non-polar solvent, if the temperature coefficient is coming negative, that is leading to the intramolecular hydrogen bonding. But previously, this experiment suggests that this is undergoing the intermolecular hydrogen bonding, and with this experiment is showing it is having intermolecular hydrogen bonding also. So it was not clear whether it is pure intermolecular hydrogen bonding or the pure intermolecular hydrogen bonding. So what they concluded is, so there is a dynamic situation at the lower temperature and the increasing concentration, it is forming as a intermolecular hydrogen bonding over the intermolecular hydrogen bonding. So to overcome that, to disrupt the intermolecular hydrogen bonding, what they have done, they have installed a heterocyclic functionality inside the system so that it will undergo for intermolecular hydrogen bonding. So then that amine NH will not be free for the intermolecular hydrogen bonding. So for that, they've started again with the compound 9. And what they have done, they have treated the compound 9 with in THF with excess sodium hydride, followed by the piconelyl chloride hydrochloride, resulting this 17 in 96% of yield solid. They have recorded the NMR 0.04 molar solution. In CD shell 3, what they found, the chemical strip value of NH was 7.6. That means the chemical strip value of 1 was 5.5. In case of 17, they got the chemical strip value of NH was 7.6. That means it is undergoing the intramolecular of hydrogen bonding. So because of that, the desilting of this proton is desilting happening and is going the downfield of the chemical shifter. And case of 10, so there was no like intramolecular hydrogen bonding. It shows the chemical strip value of NS 5.35 at the same temperature and the concentration. So that suggests that in case of 17, there is a strong intramolecular hydrogen bonding. Similarly, what they have done, they've taken this 17, they have reduced the 17 by using sodium sonoborohydrate to get the 18. In case of 18, so there is a comparison between hydrogen bonding between C4, this amide group versus this C4 hydroxy. So the chemical value of NH came down to 6.2. So that means there is a hydrogen bonding with this, but there is a comparison between the C4 hydroxy. So it's not like there is not a strong hydrogen bonding. Then they again reduce this 17 by using dibutyl boron triplet that give the regioisomer of the 18 C6 free hydroxy. In that case, again, since there is no, it's not very close to the C4 C3, so there is no competition over C6. So here again there is a strong hydrogen bonding, strong intramolecular hydrogen bonding with the 90 in the estamide group. So the chemical value of NH came to 7.4. But the whatever problem they were looking for, they were looking for the acceptor that can be C4 of the hydroxy. But whatever they got here, intermolecular hydrogen bonded one, that is the C6 one, and that known to be more reactive compared to the C4. But still, they tried the reaction of 18 and 19. In case of 19, they have taken the pre-activated sulfoxide donor with 18, and they got the disaccharide of 21, just 8% of yield. So in the reaction mixture, the 18 is not neither better, not worse than 1, is same, the estamide one. That means it is more driven by the intermolecular hydrogen bonding acceptor. So this acceptor 18 is also not good, was also not good. So to test it out the 19 hours and 20, where the C6 was free hydroxy. In same way, they have taken the donor 4. They have taken followed the same protocol. They activated the donor and added the acceptor 19. They got the 63% of yield. And in case of the 20, they got the 39% of yield. So if you see, this yield is just 50% more than the 20. So there is a role of intermolecular hydrogen bonding that will disrupt the intermolecular hydrogen bonding. That if there is no intermolecular hydrogen bonding, that will ultimately lead out to the more reactive acceptor. So once they got this disaccharide 22, so they used a hydrogenolysis condition, used a Perlman catalyst in methanol dioxane at room temperature and pressure. They deprotect all the functionality, and then they did the benzoate protection, and they were able to like purify this benzoate functionality, and that this benzoate functionality down the line can be removed in one condition. And then this 24 they got in 66% of yield. So till now, whatever donor they have used sulfoxide donor, that is the Kahn method. So also this TCA donor is also very much established in case of glycosylation. So they have taken this TCA 25 and they have activated the 25 in dichloromethane. Catalyst was dimestiflate, presence of 19 and 20 acceptor. In case of 20, the reaction went well. The reaction was smooth, but yield they got just 26% of yield. Alpha beta 1:1 mixer. But in case of 19 acceptor, there was no reaction observed with the TCA glycosylation, TCA donor. So what they have rationalized that in presence of this piconyl group, this timestabilities bind to this group with this pyridine amine, this nitrogen. So there is no more timestabilities available for the reaction. So it is quenching the catalyst. So there is no reaction with the 19. So what they have concluded is, so this installing this piconyl group is good, but this is Lewis acid sensitive reaction. We cannot utilize this one in presence of Lewis acid, but in presence of excess base, it should be compatible. So for that, what they have done, they have taken dehydrative glycosylation method that was introduced by Ginn and co-worker. So in that 27, they have taken hemiacetal. They have pre-activated this 27 by using diphenyl sulfoxide, interflic anhydride, and a 100 base like TTBP or TTBMP. And they have taken the same acceptor 19 and 20. In case of 19, here they got 87% of yield. And whereas in the case of acceptor 20, they just got 26% of yield in the same condition. That means in the basic hydrolysis and the dehydrated glycosylation method, this installation of the group which can hamper or disrupt the intermolecular hydrogen bonding uh, can increase the reactivity of the N-Acetyl donor acceptor, sorry. And further, they have used this TTBP over this TTBMP. This was costly and hygroscopy, and this was less costly and less hygroscopy. So they have used this TTBMP for further utilization. In conclusion, the reactivity, they have increased the estimate by installing the one of the heterocyclic functionality at C3. But in case of 18, where there was a competition between intramolecular hydrogen uh, with the C2 amide and the C4 hydroxy. So this acceptor or this method did not work out well. So what they told, to increase to overcome that problem, so one can put this hydrogen bond acceptor at the anomeric position. So then the C1 will be very far to C4, and then C1 can have the intramolecular hydrogen bonding with the C2, and then C4 hydroxy will be free or compete for the acceptor in the glycosylation reaction. This they have like further reutilizing or like doing the reaction, installing the hydrogen bond acceptor at the C1. In this paper, that much only they have discussed. Thank you.
Nice presentation, Bharat. So, in this work, what they are proving that in case of this NHAC, this proton is responsible for the lesser reactivity of acceptor, right?
Yes.
NHAC acceptors. So once they are showing this where inter and intramolecular, so I didn't get how actually this intermolecular hydrogen bonding is affecting the reactivity.
So what they have started with, so they have taken these three acceptor. So
Yes.
2 and 3, there is no intermolecular hydrogen bonding. Only 2 undergo for the intermolecular hydrogen bonding. So
Either inter or intra, only this one will go.
intermolecular hydrogen, not intra.
Okay.
So for that, they again modified that one only with the 12 and 14. Again, there is no NH.
Okay, so it means when they are using this either diacetate or BN substituted, so in that case, intra is not possible. So
Inter
that's
is
why
also
that is more reactive.
inter
Inter
is
is also.
hydrogen bonding, intermolecular hydrogen bonding.
Okay. And when they are utilizing this picolyl group, in that case, it is showing if intramolecular hydrogen bonding is happening, then also reactivity is increasing, right?
Then only, yes.
Okay.
So basically, so here they confirm that if there is intermolecular hydrogen bonding, so this acceptor will hamper, the reaction will not go, or the reaction yield will be very poor. So to establish there is intermolecular hydrogen bonding, they have taken these two and 3, and also they modified 12 and 14. So by this experiment, they confirm there is an intermolecular hydrogen bonding or something that is hampering the estamide acceptor reactivity. So,
Okay.
tell.
So next doubt I have, how exactly this hydrogen bonding is affecting? Like this is good observation. Like this results we are observing, but we didn't know that how actually that is happening. But if hydrogen bonding is there, how exactly it is reducing the reactivity?
Yes, so in the letter they have discussed, like in case of C41, this here.
Yes. Okay.
Here. So this group itself is quenching the Timus tiflet.
Okay.
So somehow not only hydrogen bonding, along with that something, since it is kind of basic group, whatever reaction they have done, that they have done in the Lewis acidic medium or acidic medium. Somehow the catalyst, even I exactly don't know, but maybe one of the reason. Earlier we thought like that only. Since in this paper they claim not only the because of estamide of nucleophilicity or quenching the our catalyst, along with that there is a intermolecular hydrogen bonding that is actually responsible for the reactivity.
So these promoters are affecting the promoters are getting affected with this
with
hydrogen.
presence of NHSC estimate group. This
Okay.
paper is just based on the observation. Like
Yeah, obviously this is good observation. These differences, obviously we are observing this with NHSE and 3. So
yes,
now
yes.
we have conclusion that N3 will be the best, right, among all these
Among
situations.
all the yes, azide is the best. Yes, N3 is the best.
So that is only. I also used to think why N3 is giving good reaction. Now maybe this is the reason. Even
So
Phthalimido is good only, but it is little behind from the N3.
so we are doing since like long back, but we didn't know the reason. Just we thought of it is good influence. Even though if you use TC of the NHSC, we can see after adding a lot promoter, it will not
Yes,
even undergo for hemical back or some kind of arrangement. It will be same at is that much stable TC of NHSC.
if
So
azide
it is
is there
pointing
at
something.
C2, we can use TCA comfortably.
Yes.
Okay, good, nice presentation.
Thank you.
Oh, one more thing, when they are this comparing the reactivity order, so there they have shown that again N3 is more reactive than NHSC and Phthalimido, right?
This one.
This one, okay, this is again showing the hydrogen bonding only,
Ha, ha,
right?
ha, ha.
Okay, okay, thank you.
Yeah, nice presentation, Rabia.
Yes, bye. Thank you.
Yeah. Like this, by comparing this first, second, third,
Mhm.
this NHAC N3 and Phthalimide,
Mhm.
like 1 minute.
Yeah, go ahead.
Yeah, hello.
We can hear you.
Like the only problem with this first molecule, that is this NH proton, that is hydrogen bonding, right?
Yes,
So like we have to engage this hydrogen by like only intramolecular.
yes,
So
yes.
can this that at C3 position,
Uh,
like OBN is there. So if OAC is there, so can this molecule uh, do intermolecular hydrogen bonding? Like
yes.
C.
So in presence of ester functionality, that will be not close proximity for hydrogen bonding. It should like having like if you see if that hydrogen bond will be the four-membered one. So that
Hmm.
four-membered and with this rigid system, it will not undergo for hydrogen bonding, intramolecular hydrogen bonding. That should That's why they have installed this piconelyl system. So now here see this because of this bond, it can move around and come closer to the NH group.
Hmm.
Ah,
Okay. And the second question is that like this C2N3, phthalimide and NHAC. So C2N3 and phthalimide are means working fine. Then why they are putting more effort toward this NHAC?
so the thing is, after doing the glycosylation reaction with the 2 and 3, we have to again adjust this amine functionality by using altering this groups, right? So
Hmm.
again, coming back to the NHSC, sometimes deprotection or the manipulation of the group not surviving your final compound. So that's why they are tried with the go with the native NHSC group itself. That's was the reason. Because ultimately,
Like,
once you did the glycosylation, you have to come again to the NHSC. So
hmm.
manipulation of this N3 and thalidomide is little tough, or even not needed. We can just go with the native acceptor itself. That's why they gave a effort to the
like
developed acceptor.
like this by comparing 1 2 3, if like this hydrogen is not in the first molecule, then first is the best compound for glycosylation, right?
Yes, it should be the best then.
Okay, okay.
That's what they done. They have done.
Okay,
Like
okay.
in same scenario, why they are not taking this diacetate acceptor to compare?
What they have told in the glycosylation method, the diacetate is so they told is undergoing partial deprotection. And this is the
Okay,
reason
okay.
instability of imide function in 12. And the 14 they did not took because of this rotamer.
Well, it means that diacetate itself is a not stable
Yes,
protection.
yes. No, so the thing is that if it is present in the donor, then it's fine. But in the case of when it come to the acceptor, then it's not stable.
Okay.
That's why they did not use 12 and 14. And the 16 they did not use, and they told like the preparation itself lengthy and distract. So like
What is this 14? These two amide rotamers?
this one is like now you see now is the chiral center now. Already
Okay.
this is the chiral
Okay.
system itself. This nitrogen again also become chiral center.
So
So
what problem it is creating?
the again so it's not stable as it in the like present as we are seeing it.
Oh, now it makes sense.
Yes.
Maybe similar problem I am facing because of this condition only. But in my case, it is in donor. Okay.
So 12 in donor, there is a fine, there is no problem. People have utilized a lot, like N-Diacetyl.
Yes.
But this 14, they have not utilized. And they told here also, like if compared to 1, 2, 3, 12, 14, and 16, those are the good because there was no NH bonding.
Yeah. Okay.
But people have utilized 2 and 3, not the 12, 14, and 16.
But like in this C2 and 3 one, there is a problem of selectivity in alpha beta.
There will be selectivity, but since they have utilized as an acceptor, so IISc there is no need of no worry of the selectivity.
Okay,
If
they already separated.
no, since it is present in the acceptor,
No, like this is starting molecule, first, second, third, uh, by comparing. Like, uh,
so that's what I'm telling. This
uh,
thing we are seeing as an acceptor, not donor. So donor usually affect the outcome of the product, out of the glycoside product.
okay, okay.
So, so since they have taken here the minosyl triplet, this it will depends where alpha beta they are getting. So as they have told here, they are getting beta enomer, and they characterize by using H5 chemical ship value and this C1 coupling.
Okay,
Mhm.
okay, thank you.
So here the acceptor they are just changing. So this will not too much. There will be not too much effect of the outcome of the product. So donor only we can think of.
Good presentation, Bharat Bhaiya.
I thank you.
My question is that this hydrogen bonding in NH position. So if no hydrogen bonding, then it is quenching this Lewis acid in the reaction condition.
Since we exactly don't know the reason, something is happening. Yes, we can think of one of the reason. Yes.
Okay. So if we use two Lewis acid, like one is less Lewis acidic and one is more Lewis acidic. So or we can use some more equivalent Lewis acids, some attached with this nitrogen amide form and some activate this reaction condition. So it may help.
So they also tried to like increase the loading of the catalyst or the promoter. So what happening, whatever donor they took that undergoing the hemiacyl formation. So reactivity, once it is undergoing with some kind of interaction with the promoter or because of intermolecular hydrogen bonding. So it's
Oh,
very less reactive. So it not be having as a uh, acceptor. So somewhere, even though keeping all the condition anhydrous, also they were ultimately coming to the hemiacyl formation. So we cannot
oh,
increase the catalyst loading or the promoter loading to like overcome this problem.
okay. Second thing, this hydrogen bonding is not in between of this nitrogen and oxygen of C4 one. This hydrogen bonding in which compound if intramolecular?
C2 and C3.
C2 and C3. If this is pyridine type, if not pyridine type, then how intramolecular hydrogen bonding is taking place?
That's why they cleverly install this piconylene derivative. So
Okay.
that's they have in this paper they have done. So
Hydrogen
somehow
bonding
they have
not between
disrupt the
hydroxyl group and this an amide group.
yes. Yes, their motive was to disrupt this intermolecular hydrogen bonding, and somehow they were thinking to get the intramolecular hydrogen bonding. Once it will go for intramolecular, then now this role of intermolecular hydrogen will go, and then it
Then no
can be have as
quenching
an
of this
acceptor.
catalyst.
Sorry.
Then no quenching if
Yes,
intermolecular hydrogen
yes.
bonding, no quenching of catalyst.
But same time, if you see in that case of TCA, there was a even this guy itself quenching the team stiflet.
Okay.
So again, this is not compatible with the Lewis S recommendation.
Okay, Via. Thank you.
Okay, thank you.
If you enjoyed this session, don't forget to like, share, and subscribe. We'll meet you in the next episode, next session. Thanks for watching.